My name is José Manuel Pereiras. I work for SolidWorks. I am the Territorial Technical Manager for the Andean region. So today we'll discover multi-case simulation from real customer. So the main objective of this presentation is to show you an overview of multi-cases in simulation. I won't go deeply with the details. For those who want to see more details about the implementation, I'll be here after the presentation, and it's okay for any question. Okay. All of the case studies come from my region, is Latin America. We have cases from Peru, Mexico, Colombia, Brazil, and Argentina. Let's start with the agenda. I divided the cases in 6. First, mining equipment, medical devices, LED illumination, ventilation and air conditioning, industrial equipment, and finally, this is under construction, under developing, is API for construction application. I think it's very interesting because it goes beyond a standard application, right? Okay. Okay, let's start with the mining equipment. This customer is in Peru. Fortunately, we have today here, Fernando, please. He's the engineering manager. This company is Resemin. They build this kind of equipment. So let's have a look of the main challenges that they are facing. Reduced test costs is the first one. They do many tests, so they have to simulate in order to reduce the number of them, and faster to market. They need to be mining industry is a very competitive industry, so they have to be faster. Okay, because this kind of equipment are mainly is a mechanism, they start the workflow with motion. Why? Because they need to obtain, many of you may know motion. How many of you have heard about motion? Okay. Motion give you first forces on motors. Yes, they have actuators there, so they need to get forces, power. And after that, they got forces between components. Why forces? Why they are important? Because they need to run simulation. So motion is fully integrated with simulation, with FEA. This technology is not FEA, it's multi-body, right? Multi-body simulation. So we are seeing there some overview of how motion is set. We have the motors there. On the actuators, we have 3 actuators. It's just the simulation tree. And here are the results. I'm showing now the forces on the actuators. On the right, you have a force of around 10 tons on the actuator. So that allows the customer to dimension the equipment, right? Also, as I told you, they got the forces on the components. After running motion, they do a static simulation. This is basic simulation, but it is very important because as you see here, you are seeing not only component, you are seeing also subassemblies. This is the mesh. Stresses also, This is interesting because they are getting stresses over the yield stress. This red arrow is indicating that some part of the structure is over the yield stress. So we are going to see nonlinear simulation also is needed in this case, it's necessary. And finally, displacement that is important also for their application. Okay, so the path is after running motion. As I told you, we got the finite element on different components. In this case, I will show you a very complex part. Is a chassis for the equipment. This chassis is not only under static load, is also under dynamic load. So in order to simulate those dynamic load, we have to follow every step that I'll show you. So first, we saw, as I showed you before, a static simulation, mesh, and this is interesting because they are running a 310,000 nodes. So it's a very big model, right? So that is proving that simulation, SolidWorks simulation, can face these kind of problems. After static, we go to frequency analysis. Frequency is on Simulation Professional. This is important in order to avoid resonance problem. So we are getting 26. These are the first 4 shape modes. We got the frequencies of 26, 108, 117, and 148. So if some motor, some excitator comes to this range, we are going to have resonance problem, right? So this is the first step for dynamic problem. Also, because this chassis is going over the ground, we need to run fatigue. So, and in this case, we run a variable fatigue, variable amplitude, because the ground is not, it doesn't follow a path, it's random. So we have to, this is also under developing, we have to implement accelerometers on the chassis in order to get this curve. When we get this curve, we can run this variable amplitude, or what we are seeing here in red are the most critical areas under the fatigue load. Is it okay? Any question? Okay. Finally, we have to run dynamic analysis. If we want to have a real response, okay, as I told you, frequency is the first step, but the final step should be dynamic. Why? Because we are getting the maximum displacement and the maximum stress. Look at this overshoot. And after this is simulating some impact on the chassis, and after that impact, we see a decreasement on the stresses. Anyone can guess why we have a decreasement on the stresses? Damping, yes? The damping is included in this case, and many times it's very important, always is very difficult to estimate, yes? In this case, we use, I think, 3%. And nonlinear analysis also is performed because we detected that in the static analysis that we have stresses over the yield stress, so a nonlinear static analysis was performed. So ResMin today is using this workflow. They start with motion to calculate the forces in the actuators. They follow with the static, just to have a first approach, fatigue, frequency, dynamic, and finally, nonlinear. So they are using, I think, the whole solution from SolidWorks. So the benefits that they are getting from simulation are mainly the integration between mechanism, motion, and FEA, flexible and powerful analysis workflow. As I told you, they have to be faster to market, so simulation is a great tool for them. Oops. Yes? Yeah.
But using the prototype of this one or an existing
actually, we are developing, as I told you, we are developing this analysis. This is just an example. The plan is to have a whole prototype, full scale, and include accelerometers and obtain those acceleration. You can see this at the end of my presentation. I will show you previous presentation. Last year, I presented an implementation of a bridge, concrete bridge. It is done with accelerometers, the same case. You're welcome. Okay, this customer is in Mexico. The problem with they produce laryngeal mask airway. The problem that they were having is they detected failures during inflation. This is applied for operation. You have to put inside the person, and it got inflated in order to separate I don't know, some part of the guy, right? So this is the material. As you can see here, the material is a hyperelastic. Here we have to use nonlinear simulation. Not because we are necessarily going over the yield stress. This is because we have large displacement, right? So the problem here is to identify the failure areas. Let's have a look on the model. This is a non-inflated model. This is the original model in SolidWorks. So at the bottom of the screen there, you have the nonlinear analysis. I will show you just briefly what we did. We use shell elements because it's a very thin part. So shell elements are very effective for these cases. Of course, with mesh controls. The result that it is important here, as I told you, to identify the failure areas. We got, look at this, we got 2 areas over the yield stress. On the plot, you have the red arrow over there. 8 megapascal is the yield stress of the material. So we identify it matched with the real case. Those the failure were produced in those cases, in those areas. So many times customers ask me, okay, how can I see how the finite element break? No, but it is not necessary to find this. Only if you see that the total strain is over some limit, you know that there you have a failure. These are the 2 areas that we identify. This is very important because as similar to dynamics, we got the responses. Here we have the stresses versus displacement. This is a clear nonlinear response. You see that we have a stiff material. When we reach some part of the load, the material starts to yield in some way. At the bottom, you see how the stresses increase for some part of the load. So the benefits that the customer found in this case. Failure areas were identified. Level of deformation was calculated. So engineers can make decision on this and could change the model in order to avoid these kind of failures. Of course, this type of analysis are not linear. Many settings are needed. So again, if anybody wants to see this model, I'll be pleased to show you. Oops. Okay. This is a standard case. Also, you could find, I think, on some material in SolidWorks. But it's interesting because this customer comes from many countries in Latin America. I will show you a customer from Mexico and Brazil that they are using simulation. And specifically in this case, we are going to use two modules. Thermal in Simulation Professional and flow. Yeah? The challenges here are lead overheating. I don't know how many of you have heard about LEDs. I think everyone. LEDs consume very low power, but the problem with the LEDs that they reach high temperature. So we have to try that the temperature get below certain maximum temperature. And the other challenge is airflow optimization for cooling. Okay, here we start with this customer in Mexico. This is the full device. Inside the device, we have the LED itself. It's a kind of silicon, and inside the silicon, you have the LED. This is one LED, and on your right, you have an array of LED. This is an array of 100 LEDs. Okay, if you run a thermal analysis, the problem with that we found here, not the problem, the challenge, in order to have good results, we needed to find the correct, the correct convection coefficient. Yes, every time that you perform a thermal analysis, you need to estimate the convection coefficient. So it was the first challenge, but after calculating those convection coefficients, I will show you the result. So let's have a look on SolidWorks. This is a 2 LED device. In this case, we have a different material, mainly the silicon for the LED, and some metal for the rest of the component. So this is the standard simulation tree. The material, this is a user material, so we have to, because the customer has a special LED, we have to define a user material. These are the material for some metal for the rest of the device. There you have the convection coefficient. This was obtained through the laboratory. We ran a lot of full-scale tests with the customer, but once after running this, you will see the results, and they match very, very well. These are all of the convection coefficient. You have to specify all the convection in every surface in contact with air, right? Also, mesh controls. The customer was interested on having temperatures, the full field of temperature, and over the LED, and very close, because they were having almost 150 Celsius. This is around 300 Fahrenheit. So they got many problems with the device. So I use the tool, the proof tool, that is a great tool to have to get all the temperatures and the models. And also a great tool that you can use is section clipping. You can cut your model in the middle, for example, and this is impossible to get in the real scale test, right? Because you cannot measure inside the LED. So inside the LED, we got almost 300 Fahrenheit. It's very easy to use. When you set the tool, you can, of course, it's fully integrated with CAD, so you can engineer make decision on the device, and they found the correct geometry for the LEDs. Okay, we ran basically a study problem at the beginning because it showed us what happened at the end of the process, and also the customer was interested on having a transient analysis. A transient analysis is how is switch on the LED, start heating up to reach the maximum temperature. Okay, these are the results. This result is comparing simulation temperature with full scale test. For one LED, we got 97%. For two LEDs, 98%. Almost 100% for every model. 1, 2, 3 LEDs and 60 LEDs. So we were shocked at the beginning when we saw this, because it's not so usual to have 100% of precision, right? Okay, another problem was the case of the LED. So for those problems, we have to apply flow simulation. The problem here is to define how many fins we have to use. This is a case for 14 fins. And this is for 24. We ran many cases, and what we got is that for 14 fins, we got the minimum temperature on the case. So it's a kind of optimization process that you can do with flow simulation. This is very usual. It's a very usual application from flow, right? Also, you are having conduction and convection and radiation, the three thermal processes. Also for the array of 100 LEDs, this is another type of case that we use also flow simulation. The benefits that the customer got from this is accurate result, allowed the redesign of LED system in order to have a cooler temperature distribution, and also flow analysis to define the number of fins. I think these cases come from three countries, Mexico, Colombia, and Brazil. These customers in Brazil, they produce this kind of fans. They are a kind of 1.5, 2 meters diameter, so they are very big, but they have a very specific problem. They want to find this radius in order to optimize the flow rate. It's actually what behind the scenes we were using is the Coanda effect. Yeah, the Coanda effect is we were optimizing that. The Coanda is when you have a fluid on some surface, this fluid got attached to the surface. This is the called Coanda effect. So the challenge is to improve the product performance. Okay, let's have a look on the how to set. This is flow. I will show you how to set this problem. Oops, sorry. How many of you are using flow here? Okay, many. Of course, flow, as every simulation tool in SolidWorks, is fully integrated with CAD. So right now you are seeing how we model this in CAD. This is the flow simulation tree. There we are seeing the boundary conditions. There are two boundary conditions. The first one is the volume rate. We needed to, this was provided by the customer, 40,000 cubic meters by hour. And this is a typical result from flow simulation. You see the arrow are indicating the flow direction. So in the radius, you are seeing the many arrows following the radius. So we have in flow you can define a dummy body. These dummy bodies allow you to measure some quantities, like a flow rate, for example. So we build a torus on this device, and we measure the flow rate on this torus. So we ran many flow simulations with many radius, and you are seeing there how the flow is running over the model. Is it clear? Okay. Okay. We ran two. In this table, we have 2, 4, 6. It's very simple. For every radius, we got the volume rate, and we put this information in Excel spreadsheet, and we got for 112.5 millimeters the maximum. And this is once can say, okay, this is not so important, because what could happen if I change for 100 to 112? Oh, a lot. Look at this. For 100, we have 85 cubic meters per hour, and for 112, just a little change on this big fan, we have 24 cubic meters per hour. So imagine this working 24 hours a day, 365 days a year. So it's a lot of energy. So this customer was interested on not only to build the product, also to reduce the energy. Also for selling and for marketing. Maybe I always on my trainings, this mesh is only just to show you, but it's an example. But in the production case, in the simulation, we ran a very fine mesh. This is I think these cells are very big in order to have good results. Okay. This customer is in Colombia. Actually, this is not the customer. The customer is a consultant. So they run a company who optimize in an intelligent way the flow, the ventilation, and air conditioning. So this is one of their shop. It's a shopping center. So the main challenges here were fluid analysis and comfort parameters. How many of you have heard about HVAC? Okay. We are going to talk HVAC, introducing, 2012, right? 2012. It was in the 2012. Okay. First, this is the windrows diagram. This tells you the customer the velocities of the wind that they have to consider. This simulation is considering velocity of the wind, solar radiation, and natural convection. Because in that region they try to avoid air conditioning. I know that it sounds crazy, but they do that. They can ventilate the whole shopping center without air conditioning. So it is a huge model, right? They are running not only building the model, the 3D model, also running flow as any kind of part, right? Look at this. You see here, it's a cut of temperature comfort parameters. Yes? Look at this. This black point here is a person. So they are simulating the whole shopping center with this is convection and solar radiation. What is comfort parameters? Many times, if you run flow, you have temperature, velocity, what else? Temperature, velocity, pressure. But many times you have to define, okay, is comfortable or not? So that is because we have comfort parameters. Comfort parameters tell the customer, okay, if you have a comfort parameter of X, okay, this the person that will be inside the building will be okay. If you have the comfort parameter of X plus 2, we'll have people there, most of them will feel hot, right? This customer is in Mexico. They build this kind of devices. This is found, actually, these kind of devices are found in shopping center. They are devices for high velocities. They are applied, most of the time they are on the walls, just to push air inside the room. On the right, you have I think this is more seen on offices. And this is also Coanda effect. You can find in flow a Coanda effect, the flow attaching to the wall. Okay. Although this device is very simple, I think this was one of my most challenging problems, because in this case the customer gave us a spreadsheet and said, okay, I need that the software match exactly the black points, the black dots that I have here. So these curves are, this is velocity. Imagine that you have here the device. This cylinder is a kind of room, and here you have the distance in meters. So as you go farther from the wall, you got lower velocities. So it was very hard to find because we have to use a very fine mesh, and we found a linear fitting, that allow us to have a perfect matching with the customer. Of course, after having this result, you can make changes on your device in order to optimize the problem, right? The geometry. So we have accurate velocity. These are the benefits. Accurate velocities result for ventilation devices. And the entire building analysis optimizing natural convection and comfort parameters. Any questions so far? It's okay? It's clear? Okay, excellent. Okay, let's go to those customers are in Brazil. This is industrial equipment. These are bridge crane. In this case, this customer has been producing this kind of product for many years. But the problem that they told us said, I know that my bridges are good. They have a good resistance with the loads. But the problem that they are overestimated. I want to reduce the material. So the challenges were structural optimization and the improvement of the product quality also. Okay, this is, in some way, this is similar to our first case. You remember the Resemin case. This is dynamic, because these kind of bridges take a load. In this case, the maximum load is 6 tons. So they take the load, and this load can move. Also have motors over the crane. Everything is moving. So first step, of course, motion, static, but for dynamic, first frequency. So we see here, we have the first two shape modes. Again, that tells the engineer what are the natural frequencies, and this allows them to avoid any resonance. In this case, also fatigue was run. Fatigue is simpler than the first case, because in this case we have a natural fatigue. It's not variable amplitude. It's the same amplitude always. So it's very easy to run in simulation. The main problem with, or the main challenge with fatigue is to have a good characterization for the material. If you don't have a good characterization, I don't recommend run fatigue. Also, backling. Backling is very important because, as you can see, the top part of the bridge is compressed, and this is slender, right? So you may have a backling, because in the real case it was overestimated. We got a 53 backling load factor. Backling load factor is if it is 1, it is buckle. If it is bigger than 1, it is not buckle. So 53 is a kind of safety factor. So if it doesn't buckle. Of course, a stress analysis is needed. Okay, let's have a look in this case how to set dynamic analysis, right? Oops. Okay, this is a multi-body part. You can see that we have a stiffer inside of most of these kind of bridges are constructed by stiffers and sheet metal and stiffers. And we also model the two beams at the end of the bridge. First, you have to go to the, let me, okay. How many of you are using Dynamics? Okay, excellent. In Dynamics, also my last presentation to 2012 was about Dynamics. In Dynamics, you have four modules or 4 flavors. The first one is model history. Model history is used to analyze impact. The second one is harmonic. Thank you. Harmonic, when you have a motor, for example. The third one is random for vehicles. And the last one is spectrum analysis. Okay, in this case, we are simulating a load. We are simulating a kind of impact, but it is not an impact. It is simulating that we are lifting a 6-ton load very, very with high speed, right? So we get 0 in less than 0.1 second. We got the full 6-ton load. And there we have a constant load. What we want to see is the oscillation of the bridge. So there we are. In these cases, we build some simplification. Actually, there you have some wheels, but we avoid those wheels because it is not necessary to run this analysis. So we are fixing all of those phases. After that, we are going to apply the load. To apply the load, we have to split the phase. Splitting the phase, you can put the load in one phase without any problem. So this is simulating the crane, the real crane, hanging from the bridge. Of course, you have to be aware that you have per item or total. We are using, of course, total. Don't miss that because you can have problems with simulation. And this is very important. This is the time curve. I don't know if you can see, but for 0, we have 0. For 0 seconds, we have 0 tons. For 0.1, we have also 0. It's just a 0 load. For 0.16, we go to 6 tons, and we have these 6 tons for all the rest of the simulation. For those who are using Dynamics, it's sure that you know this part. This is damping. Damping is very important. In this case, we are using 2%. For this kind of structure, they are a steel structure without many joints, so 2% is okay. Damping factor could go from 1 up to 7, 8% for this kind of structure. In this example, I'm using a draft quality in order to run faster, but for production, of course, you have to use a high quality finite element. You can see we use solid model. Also, maybe another option here is to use shell element. It's okay. But we wanted to use solid because we wanted to go further with the joints, and we want to run some fatigue on those bolts and joints. And after that, you have to run simulation. So as a summary, you have to put fixtures, damping, load, with the load, the time curve. That's it. Okay, we run the analysis. Look at this. This is when we apply here, you remember 0.1, we applied the 6-ton load. And we are having here in the center of the bridge, we are having the maximum displacement, of course. We have three zones, 3 areas. And this is very important for this kind of product. The problem here is not the stresses. The problem are the displacement. Because if the bridge is so deformed, they get stuck, right? So they have to control this ratio. If they were running only static analysis before implementing simulation, manually, right? Manually. Of course, if you run a static analysis, you will get only a certain maximum displacement. In this case, 14. This means 1/1400 is a ratio that they measure. More or less, for this kind of product, 1/1000 is okay. But when we run a dynamics analysis, we got 1/800. It is not a failure, but it got our attention because it may got stuck, right? The bridge crane. And here you have an animation. You can see how the damping effect is working because they start with a huge display, 23 millimeters, and they are getting damped, right? At the end of after 5-6 seconds, the bridge is not moving anymore. Is it clear here? Is it okay? Any question? Okay. This customer is located in Colombia. They build pump skid. The main challenge here, they were having high vibration. They call us almost crying, saying that they were getting a lot of fails on their product. So I think we helped them. Arturo, is okay? Right? Okay. So can you see these flags? On these flags, they implemented accelerometers. Imagine the cost of this, right? Because they were having a lot after building the product, after selling, they got those problems, and they have to instrument all the pump skid with accelerometers. They put accelerometer in those locations in order to get the acceleration and trying to understand what is going on. This is the real result that they got. These peaks here identify as they were running the pumps, and they were getting some peaks, and with those peaks they identify the resonant frequencies. We ran simulation, and we saw that we have a surprise here because our simulation it doesn't have the same result that we were having on the field, right? So we start investigating what's going on here, and we found that the sun support. these are some piping over the skid, and this is the frame, right? So when we did some investigation on the model, we find that some supports were missing because corrosion, because I don't know why, but they were missing. Some fracture on the concrete. So that was the reason why they got lower frequency than us. So their model was a kind of softer model than our model. Of course, this is a real case. The engineering decision was easy, right? They have to put the support and to rebuild this column. So structural optimization, in this case, 30% of material reduction on the bridges, and improvement in product quality, around 40% better compliance on their products. Okay. Finally, I want to talk about this. This is not finished, so this is under developing. But I think it's very interesting because how many of you have heard API, the concept of API? Okay. API is application programming interface. This is useful when you don't have the specific tool in SolidWorks or in simulation. So I will show you what we are doing here. So this is my customer. They have two teams, the simulation team and the design team. They are working independently, so they are having a lot of delays in their project. So we are building API. API is programming in this case in Visual Basic, embedded in SolidWorks. Also, I think you have 3 or 4 sessions here of API. You can program in Visual Basic 6, that is embedded in SolidWorks, or you can program in Visual Studio.NET. In this case, the strategy is they have, of course, SolidWorks. Because they are civil engineers, they have a lot of Excel spreadsheet for calculus, like steel bars, concrete, whatever. Civil engineers love Excel. And what we are doing now is an interface that interacts with SolidWorks, SolidWorks CAD, SolidWorks simulation, and SolidWorks drawings. And is interacting also with Excel. So that improves the workflow of this customer. So with SolidWorks, they are getting 3D models, documentation, and bill of material, the standard stuff that you get from SolidWorks. The API from the interface, they will have a model generator, I'll show you, a specification and calculation, some special calculation. For the Excel, they will reuse this API will allow us to reuse. Of course, for those that are taking note, it's okay, but this will be available I think in 2 months. The PowerPoint and the videos. They will reuse Excel spreadsheet, calculation and documentation from Excel. So, the API is focused on this kind of, these are foundation. So we are going to see this application very focused on this kind of problem. So for the API, we have a form for 3D model generator. Calculation, Excel and simulation. We have to interact with Excel and simulation because it's a requirement. Here you have, this is very interesting because not only concrete for foundation, we are also calculating the steel bars. And finally, documentation. At the end of the day, they need the drawings. That is the final documentation that they need. So let's have a look at how this is working. Of course, this is a draft, but this is the form. First, this is in some ways basic to do. It's simple to do and through API. They don't need to model every time the foundation. They have the form, and they have to fill the form, and they have the 3D model. So as you can see, the model updated with the new dimension. Not only it is updating the geometry, it is updating the calculation. So behind the scenes, it is the simulation is run, and you got all the simulation results. So it is not needed to go to simulation, to put the fixture, the loads. Everything is done automatically. After doing this, maybe you can change the load. Maybe you need to change the load. So also you have an interface to put their loads in tons. In this case, I'm going to Excel because it's a simple case. So this API is interfacing with SolidWorks, interfacing with simulation, and it's interfacing with Excel. Here we have 20 steel bars. They are calculated by their Excel. So with these 20 bars, what they were doing, they have to do manually every documentation. In this case, everything is integrated. As you can see here, the customer can set how number of layers they want. So in this case, we are going to use only one layer. And this button is to include the steel bars on the 3D model. So this steel bar goes to the, imagine to build this manually. It took 1 week in order to have the full documentation. Right now we are estimating when we finish this implementation, it will take 2 hours, only 2 hours to finish everything. So you got all the foundation with all the steel bars done. And finally, what they need is drawings, right? This is the final documentation for the field. So they have all the steel bar in place. And of course, this is native SolidWorks. This is not necessarily any API. And of course, the bill of material. All the volume of the concrete and the number of a steel bar and the diameter. Okay, finally, for those cases that are more complex, that they don't have an Excel spreadsheet to calculate the steel bar, for example, or of the dimension of the concrete, we have to run a simulation. I don't know how many of you are aware about this kind of fixture. This is elastic. This is an elastic fixture. This allows you to simulate soil structure interaction because it takes into account the stiffness of the soil. So after running the simulation, this is not a fix, this is not a roller, this is not a hinge. It's a special fixture that simulates this soil structure interaction. So for those cases, we use the API of course, with simulation as an engine. So the benefits that they got were time reduction in project development, as I told you, from 1 week to 2-3 hours is a lot. And leverage of API power in SolidWorks simulation. Okay, let's do a resume of this. Real customer simulation. We saw motion and FEA integration. This is great in SolidWorks simulation. Also, we saw static and fatigue. You remember variable amplitude and harmonic, both of you. We saw frequency and buckling. Frequency, the first step for dynamics, and buckling for those cases that are slender and under compression. Thermal for LEDs, for the LEDs company. Linear dynamic and nonlinear for many cases like resemming. And finally, flow and HVAC for those cases of ventilation and air conditioning. So that's all. Here you have my information. Here you have my previous presentation in 2011 and 2012. And thank you very much.